Indeed, here's the question for today. Is a mass on a vertical spring a simple harmonic oscillator? Okay, let's analyze this situation by considering a spring hanging from a ceiling, and then we're going to place a mass on it. And then we're going to let it oscillate and see if it's a simple harmonic oscillator. Remember, of course, that the definition of a simple harmonic oscillator is that there is a restoring force, which is in direct proportion, but the opposite direction, k SHO times x, to its displacement from x equals 0, which is the equilibrium position of the SHO. We also have a separate equation that applies to springs called Hooke's law. And Hooke's law says that the force exerted by a spring is negative k spring constant times x, where this x is how far you've stretched it from the unstretched length. So realize that is not the same as the equilibrium position of the SHO. We're going to use that expression to analyze this mass on a vertical spring. And so we're going to have to be very careful to keep the x's, the k's, and the f's all straight. So in fact, because these x's are different, I'm going to call this one over here x SHO. That's where 0 at equilibrium of mass on spring. And I'll draw these in a second. And x SPA is 0 at the unstretched length. All right, so we had the spring hang from the ceiling, and then we're going to attach a mass to it, which is, of course, going to stretch the spring somewhat. And so I'm going to draw the mass now hanging from the spring at equilibrium at that position. All right, let's start labeling some stuff here. Give myself a little bit more room. All right, we start with the bottom of the spring right here when there's nothing hanging on it. This point right here is where x SPA is equal to 0. Then we have another interesting position, and that is the same point on the spring down here at the equilibrium position with a mass on it. If this, in fact, is a simple harmonic oscillator, which, by the way, it will be, this would be the position where x SHO is equal to 0. So there, these two values, the x measured for the spring constant and the x measured for the simple harmonic oscillator, have their origins in different places, and we don't get to choose where to put them. Those are there by the definitions and the equations that we're using. Okay, then I'm going to draw one more picture of this thing, and that's going to be when I've displaced it from its equilibrium position. So I'm going to stretch it farther down. There's my mass. And release it from there or something. And this is I'm going to use this picture to analyze the forces and decide whether or not there's a restoring force which is in linear proportion to displacement from equilibrium. All right. So let's write some equations and let's define some terms. Let's also, before we start, define our positive direction, which it's convenient in this case to make the positive direction, the positive x direction down, and actually, again, have two different versions of x that have their origins in different places. And again, I have to keep them separate. But I'm going to make the down direction positive for both of them. Okay, let's analyze this equilibrium position in the center here. And in the equilibrium position, we do know, of course, that the forces are balanced because it's at equilibrium. And that means that the downward force of gravity is the same magnitude as the upward force exerted by the spring. I'm going to put kx there, and then I'm going to have to make sure I know what k and what x this is. This k is a spring constant. This is k SPA. Because all I'm doing right here, at this point, I'm saying nothing about whether or not it's a simple harmonic oscillator. I'm just saying, oh, gee, there's balanced forces, mg down and kx up. So this is k SPA and x SPA. So in other words, that x is how far the spring has stretched from the position where there's nothing on it, and I'm going to indicate that here. And this value of x SPA is actually a fixed value for this mass because it's how far this particular mass stretches the spring. And so I want to give this a name that doesn't make it look like a variable. And so I'm going to call it big capital X, big X. And that big X is the amount the spring stretches when this mass is at equilibrium. So again, for this particular mass, that's a fixed amount of distance. So I'm going to rewrite this equation. mg equals k sp times big fat X. And that's the amount of stretch when the mass is at equilibrium. Okay, we've said nothing yet about whether or not this is a simple harmonic oscillator. But now let's examine, actually no, I'm not going to do that yet. The other thing that I want to do is relate these two coordinate systems to each other, where x sp is equal to 0 and where x SHO is equal to 0. And we can see here that where x, they're related to each other because they differ by this value big X. And so basically, where x SHO is equal to 0, the value on the x sp scale is big X. So I can make I can relate these two to each other by saying that x SHO is x sp minus big X. So let's make sure that that makes sense. Measuring on the x sp coordinate system, so starting from here, the value of this point down here that I'm just marking with a red dot, on the x sp system, let's say big X is 10 centimeters. Okay, on the x sp coordinate system, x sp down here is positive 10. So x sp is positive 10. X SHO, though, at that value is 0 because I'm on the origin for the x SHO axis. So therefore, the x sp value is bigger, and to relate them to each other, I have to subtract 10 from the value on the sp axis to get the value on the SHO axis. So the SHO value is also going to be 10 less than the x sp value on those axes, on those coordinate systems. Okay, so that's how these are related to each other. And so I'm going to be using that in a second. Now let's go over here and examine the forces on this mass when it's oscillating. So in the third position over here, because we want to find out, is this the SHO? Is there a restoring force which is in direct proportion to the displacement, this is x SHO, from the equilibrium position? Is this true? And if it is, and so this k is k SHO, what is the proportion, the proportionality constant that relates the amount of displacement to the restoring force? And we saw in class, for instance, when we did a pendulum, that that value of k was mg over L or something like that. So we're going to find out by analyzing the forces, what is that k value for this particular oscillator? All right, so let's examine the forces. If I find the net force on this object at this time, there are two forces. There's, of course, mg down, which is our positive direction, and there's a spring force, which is k sp x sp exerted in the upward direction. We've made down positive, so I'm going to write the net force here as mg minus k sp x sp. And we're wondering if that fits this description of a restoring force that is in proportion to the displacement from x SHO, where x SHO is equal to 0. So what I need to do now is do some substitutions. The first one I'm going to do is, conveniently, I see over here from our analysis of equilibrium position that mg is equal to k sp times that constant x, which is how far the spring stretches at equilibrium. So I'm going to say net force. I'm going to sub in for mg. I'm going to sub in k sp times x. Then over here, I'm going to do k minus k sp times x sp. But x sp, from the relationship between those two coordinate systems over here, x sp is equal to x SHO plus big X, just C-fooing this guy over here for x sp. So I'm going to sub in for x sp, x SHO plus big X. Okay, this is a big X over here too. All right. Okay, let's do a little bit of algebra. Net force is equal to, I'm going to distribute that, k sp times big X minus k sp times x SHO and then I've got minus K SPA times big X. Well, hey, looky here. K SPA big X minus K SPA big X, those go bye-bye, and I'm left with the net force on this block is negative K SPA X SHO. And remember what we're trying to do here, we're trying to find out is, where are we here? Is there a restoring force which is equal to negative K times X SHO? And is this true? Question mark. And now I analyze the forces and I say, well, golly gee, it sure looks like it, because I have a net force on this thing which is equal to a constant times X SHO. What is that constant? Well, golly gee, the constant, that's what I lost when I moved this thing. This is K SHO. The constant, the thing that I find in this red, now a red box, in front of the X SHO is K SPA. So, interestingly, the constant for the simple harmonic oscillator, K SHO, is equal to K SPA. So the spring constant turns out to be numerically equal to the constant used in all of our simple harmonic motion equations. And we end up, in fact, by saying, well, the period, for instance, of a mass oscillating on a vertical spring is 2 pi root m over K SHO. That's the general form for a simple harmonic oscillator. But what do we plug in? We plug in K SPA. So it's kind of subtle. We can't just look at this and say, so this subs into be K SPA. We can't just look at a vertical spring and say, oh, it's a simple harmonic oscillator because it's got a mass on a spring. Because, in fact, there are two forces. But as it turns out, through analysis of this derivation that we just went through, it works out beautifully that the constant proportionality is a spring constant, and you end up with the period is equal to 2 pi root m over K SPA, and that is that.